to the third person, like,
Alright, so 2E. Alright, so 2E says we're going to build the composition f of h of x. So I'm going to start with h of x, which is 3 times 2 to the x. And then I'm going to take that and plug it into f. So f is 4 times 3 times 2 to the x minus 5. So cleaning that up, can I multiply the 4 and the 3? Absolutely, there's no reason I can't. Can't multiply the 2 though, because it has the exponent. So 12 times 2 to the x minus 5 would be your answer. Okay, Anna?
Yeah.
Okay. Anybody else on 2-7 or 2-8? Raina?
On number 3.
Or which paper?
Oh, 2-7.
2-7, number 3.
For the function n one, what would that, like, can you do that one? Like, what would the function n be?
What would function m be? Alright, so I'm taking my g function. Okay, here's my g function. And I'm doing something to it. It has a vertical dilation, that means it's a multiplier, it's a stretcher. Verticals for the out in front. It has a vertical translation, that means literally picking it up and moving it, down 3. And it has a horizontal translation of positive 1.
Okay.
So that would be your function.
I didn't see that you had added to g, so.
Yeah, you have to have an original if you're going to translate it or whatever, yeah. Alright, anything else 2-7 and 2-8?
on 2-7, problem 3, letter C.
3C. Another composition. It says find P of f of pi. So f is the picture, and pi is like 3.14, but everything from 3 to 6 all has a value of 2. So f of pi will be 2. Can you see that from the picture? And then I'm going to plug 2 into P. So what's P? Oh, P is the chart. So when I let x be 2 in the chart, the answer is -1. Anybody else on 2-7 or 2-8? Xander?
Can you do 2-7 odd, please?
2-7, 3i.
Yeah,
Is that what
yeah,
it was?
yeah.
3i?
Yeah.
Alright, so it says find m of f of p of 9. M of f of p of 9. Okay, so I'm going to start with p of 9. And p is the chart. So p of 9 is 3. Right?
Yep.
And then I'm going to take that 3 and put it into f. F is the picture, and f of 3 is 2. And then I'm going to take the 2 and put it into m. So remember, this is m. So when I plug 2 in there, that's not plugging in, right? So that's going to say 2g of 1 minus 3. Because I'm putting 2 in right there. So what's g of 1 G is another picture, and G of 1 looks like, what, 3/2? And then 2 would be, 2 times that would be 3 minus 3, I got 0. Is that what I'm supposed to get? Let's see, is that what I got before? Yeah. G of 1 is 3/2 times 2 is 3 minus 3. All right, anything else? Alrighty, so tomorrow we just have a little quiz. It won't take long at all. Just a little one. And today we're going to look at 210 and probably some of 211. Exponential functions and logarithms are inverses, so we would expect their characteristics, input output for exponential to become output input for logarithmic. Does that statement make sense to you? Yeah, because the x's and y's get switched, right? So let's look at that first little chart there. Notice how the input values are changing additively, that is, they are equal spaced input intervals, while the output values are changing multiplicatively. So timesing by 2 each time. So we know that is characteristic of an exponential. We know that. Now think about that for a second then. What is a logarithm table going to look like? Those get flipped. So your x's aren't going to be equally spaced, are they? What are your x's going to be doing? They're going to be multiplying. And then your y's are going to be adding, right? Okay, so that's the key. So now let's look at example 1. Determine if the given function could be logarithmic, exponential, or neither. So in table A, what's happening to your x's? Going up by 1. What's happening to your y's? Times by 1/2. So when your x's are equal spaced intervals and your y's are being multiplied by something, then you know you are exponential. Right? Let's look at B. What's happening to the x's? They're being multiplied, and the y's are being added. That is a characteristic of the inverse of an exponential, which is a logarithm. That's a logarithm. All right, what about C? X's are being times by 10. Y's are being times by 2. That's neither. That's neither. It's not exponential or logarithm. It's nothing that we know at this point. All right, what about D? That's logarithmic, because the x's are being times by 2, and the y's are going down by 3. All right, example 2. show that f and g are inverse functions by showing that their compositions equal x. Remember, that's how we prove things are inverses. This must be the case, and this must be the case. Some of you didn't do such a good job of this on the homework, and I wrote GTQ, guaranteed test question. That's one of the main ideas, so make sure that you understand if you are to show that two things are inverses, this is how you do it. Okay, so what are my functions? F is 3 to the x, and g is log base 3 of x. So what does this say? What am I supposed to do here? Give the f into the g. So g of 3 to the x would be log base 3 of 3 to the x. Would you agree with me on that? Now, do you know what that equals? That actually equals x. Now, why? Why does that equal x? Well, let's pull this off here for a second. And let's suppose you had this, and you wanted to know what that equals. That's our job. What does this equal? Okay, I don't know what that equals, so I'm gonna set it equal to a. And then if I log roll it, look what it says. What does that a have to equal? X, yeah. So this is actually one of your properties of logarithms. When these two numbers match, that's the answer. So if you had log base 7 of 7 to the 5th, that would be 5. If you had log base 8 of 8 to the negative 3rd, that would be negative 3. It's always that. Okay, perfect. Now we gotta go the other way. So this one worked out great. This one came out the way we wanted it to. So now we're gonna do this one, which says find the f of the log base 3 of x, which is 3 to the log base 3 of x. Do you know what that equals? It actually equals x2, and let me show you why. This is another property of logarithms. 3 to the log base 3 of x is just going to equal x. 5 to the log base 5 of p will just equal p. 8 to the log base 8 of 19 will just equal 19. Now why is that? That is a property. It absolutely is true. Why is it? Let's look and see. Figure it out. We want to know what this equals. So I think what I'll do, this is going to look kind of funny, but I think what I'll do is take the log base 3 of both sides of the equation. Perfectly legit. You're allowed to do that. And then the exponent is going to come off out in front. Now, we just talked about this one. What is the log base 3 of 3 to the first? 1. So now it says the log base 3 of x equals the log base 3 of a. So what did this thing equal? Yeah, absolutely. Keep those two properties in your back pocket. B to the log base b of m equals m, and log base b of b to the n equals n. Those are valuable and can save you a bunch of time if you recognize them. All right, sketch a picture of the inverse of the exponential. Take a minute and do that. You know how to sketch inverses. Sketch the inverse of the exponential that they graph there.
Bless you.
Okay. I got my red picture. Is that what yours looks like? So this is your exponential curve, and this is your logarithmic curve. This is the equation of y equals log base 2 of x. That is the inverse of the exponential. So I guess I'll write the inverse. Okay? In general, logarithmic curves, exponential curves increase and are concave up. On the other hand, logarithmic curves increase, but they are concave down. Example 4. The exponential function contains these 2 points. Find the average rate of change of the logarithmic function over the interval from 3 to 27. Take a minute, think about that, talk it over with your partner, come up with an answer. This is one of those problems that can seem really, really hard, but it's actually really, really easy. What do we know about the ordered pairs of inverses? The ordered pairs of inverses are switches of each other. So when we find an average rate of change, don't we take our y values, change in our y values over the change in our x values? So for the logarithmic function, these would be the ordered pairs, and this would be the average rate of change. In other words, it's the reciprocal of the rate of change of the original, because your y's and x's got flipped. So you could have found the average rate of change of the original points, and then flipped it over, because the y's and the x's. Is that okay? Easy peasy. All right, let's look at the mystery function real quick. See if you and your partner can fill in any of the, based on what they gave you, can you fill in any of the other points, the missing blanks? What's going on yet? What's happening, Riley?
It's the basis 2 and the y, the x1 is to get to the x's.
Perfect. Perfect, that's what's happening. 2 to the second is 4. 2 to the negative first is 1/2. 2 to the fourth, 2 to the third, and so on. So, what y is going to go here? What y is going to go here? Perfect, 0. 2 to the 0 is 1, right? All right, how about here? Negative 3, very good. 2 to the negative third. Here. 6. Here. Think about what that's saying. That's saying 2 to some power has to be 0. Is that what this one's saying? Can you do that? Can you raise 2 to a power and get nothing? No. No. And you know why? Because this is your logarithmic function here. Okay? And in a logarithmic function, because this would say log base 2 of x equals y. That's really your equation. There's an asymptote at 0. Remember, it looks like this. X can't be 0. So that one's not possible. All right, what's this one? Negative 2. What's this one? Now think about it. It's saying 2 to some power would be negative 1. Is that possible? No, you cannot raise 2 to a power and get a negative. So again, x can't be negative. There's no x's over here. So that's another no. How about that last one? Can we raise 2 to some power and get 3? Is that possible?
Yeah.
Yes. Now, it isn't going to be an integer, like 2 or something, right? But we can do it. We're just going to need some calculator help to figure that out. Would everybody agree with that? Okay, so we'll figure that out in a minute. All right. This person believes that this point is on the graph of the function. Well, we could check it real easy. Take your calculator and raise 2 to the 4.585 power and see if you get 24. I think you do, actually. It won't be exact because it's a round off. It's really close. So, is he correct? Yep. 2 raised to the 4.585 power is indeed 24. How are the outputs for 8 and 1/8 related? They're opposites, right? They're opposites. Why do you think that happens? Because when exponents are negative, this is an exponent. When exponents are negative, your base is flipped, numbers flip. All right, this other person thinks that the output for 3 would be 1.5. So in other words, 1.2 to the 1.5 is 3. Now I want to talk about that for a second before we type it in on our calculator. First of all, do you understand what this person's thinking? 2 to the first is 2, and 2 to the second is 4. So this person's thinking 2 to the 1.5, then would be 3 because it's right in the middle. So I understand that logic. What's wrong with it, do you know? This would be a linear relationship. And is this a linear thing? No. So what is 2 to the 1.5? 2.8? So how can we figure out what this number needs to be? 2 to the y is 3. Take the log of both sides, absolutely. Or ln, it doesn't matter. And the log of 3 divided by the log of 2 is going to be the answer to the question. 1.585. We should have known that. We should have known that. Because we already figured out that the log of 24 was 4.585. And the log of 24 is 3 times 8, which is the log of 3 plus the log of 8. And what's the log base 2 of 8? 2 cubed. Log base 2 of 2 cubed is 3. So log base 2 of 3 plus 3 equals that. So the log base 2 of 3 has to be 1.585. Yep, I totally missed that first time. All right, back side, here we go. Here we go. Take a second with your partner. See how many of these you can answer. You will not need a calculator for any of it, I don't think. I don't think you'll need a calculator for any of it. doing?
You have to do it one day.
Do my answers match yours for those first 5 in number 1? Now, I chose to do them with one of the properties we talked about. Let's say number 4, for example. You could log roll that if you wanted to. 10 to what power is 1 over 100, and you're gonna get -2. So all of these could actually be log rolled if that's easier for you. Set them equal to x, and then rewrite them in logarithmic form. All right, let's ask if we have a question. Does anybody have a question about any of these 5 problems right here? Everybody got all those answers, right? Somehow, one way or the other, you got them right, perfect. All right, the charts, I don't know, that seems pretty self-explanatory. This one is the inverse of that one. So notice that the y's became the x's, except for that last one, it got a little weird. And then, the x's became the y's. Is that okay? The relationship between F and G are inverses, definitely. Let's find the compositions, okay, we can do that. We're gonna do B in a second, but let's talk about C. As the inputs of F grow, what are, the inputs of F are going up by 1, so they're growing additively. What's happening to the outputs? They are growing multiplicatively. And then for G, this is function G, the reverse is true. The inputs are growing multiplicatively and the outputs are growing additively. Okay, let's build the compositions to prove that they're inverses. And then we'll be done with this. And what will happen, this is what I'm trying to show is going to happen. All right, so F is 3 to the x. So log base 3 of 3 to the x. What does that equal? The log base 3 of 3 to the x. Right? That's one of our properties. We're not going to be confused by that. And then the other way, we're going to plug G into F. So that's going to be 3 to the log base 3 of x. And that is also, we need it with inverses though, before we start it. Okay? Alright, we're going to do a little bit in 211, and then we're going to hopefully have a little bit of time for some review. Alright, so 210 is due on Wednesday, and we're going to start 211. Not do it all, but we're going to start it talking about some of these main ideas. So read through that first, all that textbookish type stuff. So that first part talks about the importance of this number out in front. He calls it A. This is your regular logarithmic function. What happens when you put a negative in front of anything? Flips it upside down, so doesn't that make sense? So the asymptote is still there, the asymptote is still at 0. Everything has been flipped upside down. All right, that makes perfectly good sense. Perfectly good sense. Now, what I want to investigate is what happens when your base is not bigger than 1. So notice that he stipulates in both of these examples that your base is bigger than 1. In fact, I was using a base of 10. But it would be true no matter what the base was, 5, 4, whatever. Those are the pictures. What happens, your base must be positive, but what happens when your base is something like 1/2? Well, how does that change the picture if your base is 1/2? Do you have any thoughts on that, or do you have an idea how we might figure it out? I don't think very well in logarithms. I always want to change them into exponents. So what if I changed this? This is what I'm graphing. But what if I changed it into its equivalent exponential form, 1/2 to the y equals x? Same equation, but this makes more sense to me in terms of plotting points. Okay, so pick a y. Pick a y. 1, 2, 0, -1, -2. Let's just start with those. Now, those are y's. What's 1/2 to the first? 1/2. What's 1/2 to the second? 1/4. What's 1/2 to the 0?
1,
1/2 to the negative first.
2,
And -2.
4.
Okay, let's plot those and see what this thing looks like. So, 1/2, 1, 1/4, 2, 1, 0, 2, -1. What's happening here?
Exponential decay.
Well, no, it's not exponential decay, it's a logarithmic curve. It's a logarithmic curve. But it is going down. It is going down. And what does it look like? Have we seen anything like 2 minutes ago that looked like that? Doesn't it look just like that one? Where did we get that one from? How did we get that? We put a negative out in front of the problem. Okay. What happened in this one? Isn't 1/2 2 to the negative first? So this equation says 2 to the negative y equals x. So in logarithmic form, it would say negative y equals log base 2 of x. And if I divide off the negative, oh my gosh, isn't that exactly what happened here? So, if your base is less than 1, it's going to have the same graphical impact as making your curve negative, flipping it over. Joe Funk, is that not like one of the coolest things ever?
I'm on drawing.
I know. All right, quickly, example 1, let's go through this and see what we can get figured out. Notice that for our end behavior with a logarithm, we can't go to negative infinity. We can only go to 0. So as we approach 0 from the right, what happens to our curve? Negative infinity. As the limit as x approaches infinity is positive infinity. Yep, so your end behaviors, the limit as x approaches 0 from the right, because that's as far as the curve can go. So what about for B? On the left side, we're approaching 0. What is our limit for problem B? As we approach 0 from the positive side, from the right side, positive infinity, yep. And what about on the right side? As we go to positive infinity, what is our curve doing? Negative infinity. All right, figure out C. There's no picture. Use what you know so far. This one gonna be going up or coming down? Going up. How do we know? Positive number, base bigger than 1. That's what they look like. So what's your end behavior? The limit as we approach 0 from the positive side is negative infinity. And the limit as we approach infinity is all right, I'm going to pause there. And then we do a couple quick review problems. So last time we did a couple from this little one-page review, 2728 review. Let's look at station 4, because that one looks like a potential quiz question for tomorrow. So on this one-page review that everybody got, we already did the first couple, now we're doing station 4. The graph of the function f is drawn, a table of values for h is given, and g is square root of 14x minus 3. Okay. Find h of f of 4. All right, who can do this for me? H of f of 4. What's f of 4? 3. What's h of 3? Perfect. F of h of 3. All right, what's h of 3? 5. And what's f of 5? 4. Yep, 4. Perfect. All right, do C and D. Okay, C was pretty easy. What'd you get? 5? 5? Alright, what'd you do with D?
Switch the values.
Switch the values. So if we want to know what the inverse value of 4 is, then we want to know what input originally gave me 4 to start with.
Yeah.
So if I look at function h, it looks like 2 gave me 4. So when I do the inverse of 4, I'm going to get my 2 back again. Perfect. Same thing with e. You don't have a chart there, but you need to figure it out. Can you figure it out? I heard somebody say it, I think.
It's
6, yeah. What do I plug in to give me 9? That's basically what I'm trying to figure out. Because the inverse would take that 9 and give me that number back again. And it's 6. And then I'm not sure, I haven't done F. I'm not sure why it's a challenge. Has anybody done it yet? Is it a challenge? No? What's H of 2? Where's H? H of 2 is 4. And then F of 4 is 3. And then G of 3 is root 39. Did I do that right? Yeah, I don't think that's a challenge anyhow, but there it is. Anybody have any question about that? All right, you are golden. Good job. Little quiz